Right, time to look at our last family of functions, the inverse trig functions, and that'll complete the suite of all the different functions we look at in this course. So the inverse trig functions, let's create them. So first of all, inverse sine of x, well, it must come from y equals sine x. So there's my sine curve. So it has domain or real x, and it has a range in between -1 and 1, but of course it fails the horizontal line test, so no good, doesn't have an inverse. So we need to pick a domain to restrict this on, and the idea was we wanted to try and get 0, try and get the whole range if we can, and if we have to make a choice we'll go with the positives. Well, the piece of the curve, what we really need is one piece of the curve that simply goes from the bottom to the top or the top to the bottom. So there's several pieces we could pick there. But if I want to include the origin, I suppose the logical spot to pick would be from minus pi on 2 to pi on 2. Now, that means that the whole range stays in play. The inverse then is y equals the inverse sine of x. Now, again, I mentioned this yesterday, but this explains why we have the reciprocal graphs. Because where the -1 is, meaning inverse function, is also where we place the power of a trig function. So we never use negative indices with trig functions. Otherwise, we're going to get confused. Am I talking about the reciprocal of sine x, or am I talking about the inverse of sine x? So if we see that -1, we know we're talking about the inverse. If I want the actual reciprocal of sine x, well then I use cosec x. Its domain will be the old range, and its range will be the old domain. Now this explains why on your calculator, when you're going inverse sine and getting answers out, the calculator only gives you acute angles or negative acute angles, because it's basically reading off the inverse sine function. So it can only give answers out between -90 and positive 90. What does it look like? Well, let's draw in y equals x there. Because of the scale, it's a bit hard to reflect that one, because you see where 1 is on my y-axis as opposed to pi on the x-axis. So I'll just draw it to the side here. If I have to draw an inverse sine graph, then basically I just mark in these 4 points. So pi on 2 minus pi on 2 minus 1 on 1. And we're basically drawing a sine graph, well that was an attempt to draw a sine graph, but winding along the y-axis rather than the x-axis. So it's just a piece of it. Now, it's not a cubic, it's not a tan curve. Because remember, here at pi on 1 pi on 2, that would be, it's not a stationary point, we'd have a vertical tangent, because the original graph would have a horizontal tangent. So that's coming to sort of a peak at that point. This is where math aids come in real handy, because you can just get it and draw that piece of the sine graph sideways. Okay, let's do the cosine, or inverse cosine. So we'll draw up the cosine function to start off with. So again, fails the horizontal line test. Domain's all real x. The range again is -1 to 1, so no inverse. I'm going to have to pick a different piece. Again, I want to get the bottom to the top, that piece of the curve, but if I go minus pi on 2 to pi on 2 this time, it's not going to work, because I'll just get that, upside down U shape. That's no good, because that'll still fail the horizontal line test. So for inverse cos, we're going to restrict the domain of the cosine function simply between 0 and pi. So therefore, when we talk about the inverse cos function, the domain will be the old range, -1 to 1. The range will be the restricted domain, so between 0 and pi. And now that explains why with your calculators it will give you obtuse angles, because its function gives answers out between 0 and pi. So that's what the calculator is reading. Well, what was this one look like? Again, a bit hard to do it on the same scale. So let's draw it to the side here. Mark in those 4 key points. So this time it's going from 0 to pi. It winds around the pi on 2. But again, it's a cosine curve on its side. it's surprising how often, and it's a mistake of course, people flip this curve because they think, oh, positive must go with positive at the start here. But if you read it properly, cosine of pi is -1, not +1. So it actually goes in that direction. Alright, let's complete the suite. Let's look at inverse tan. So there it comes from the tan graph, of course. So let's draw that one up. Once again, fails the horizontal line test. Domain is that interesting one where we've got these continual discontinuities. That's probably a bad way of expressing it, isn't it? We've got the repeated asymptotes. That's probably a better way of saying it. And the range is all real y. Well, again, fails, but I hope it's quite obvious which piece we're going to pick, because the asymptotes sort of separate them quite nicely. If I go from minus pi on 2 to pi on 2. So I'm going to restrict it, but they're asymptotes because notice it's not equal to as well. So it's just less than, not less than or equal to. That'll give me the complete range. So consequently, our inverse tan graph, domain will become all real x, and the range will go in between minus pi on 2 to pi on 2. We'll now have horizontal asymptotes at those points. Let's draw that one. So for that one, we'll draw in those horizontal asymptotes, and we get the tan curve on its side, if you like. There's inverse tan x. So they're the three basic inverse trig graphs that we work with. Now, as I say, looking at those graphs, we spotted inverse sine was an odd function. So we can say inverse sine of -x is equal to the inverse sine of x. The cosine one's a little bit more interesting, because when you first look at the cosine graph, it doesn't have rotational symmetry about the origin, and it doesn't have line symmetry either. But it does have rotational symmetry about pi on 2. So if we shift the whole graph down pi on 2, we can create an odd function, and that ends up with creating this identity. The inverse cos of minus pi on x is equal to pi minus the inverse cos of x. Now you may be thinking, hang on, where's pi come from? We're only shifting at pi on 2, but there's a shift happening on both sides of the equation, so it's like 2 lots of pi on 2, and that's why we end up with pi there. So basically we've got our odd function shifted, well, I said shifted up pi on 2, so whichever way. Inverse tan is a little bit more straightforward. It was just an odd function as well. So we get inverse tan of -x is the negative inverse tan of x. And I guess the other one we sometimes use is this one here. Inverse sine of x plus inverse cos of x will always equal pi on 2. I suppose the easiest way of thinking about that is a right-angled triangle. If you've got a right-angled triangle, obviously one angle is a right angle. Now, the other angles, one of them will be the inverse sine of x, and the other one will be the inverse cos of x. And so they must add up to be 90 degrees. Now that's not a proof, but that's a way of thinking about that. So the two will always add up to be 90. It's the complementary ratio idea, meaning complementary. So basically it comes from an angle sum of a triangle. Alright, let's find the exact value then of inverse tan of root 3 minus inverse tan of 1. Notice they haven't specified radians, degrees or what have you. We always assume radians. So inverse tan of root 3 is pi on 3. Inverse tan of 1 is pi on 4. Do the subtraction, we get pi on 12. So inverse sine of 1 on root 2, so that'll be pi on 4. But then we've got minus the inverse sine of minus a half. Well, alright, we could find the inverse sine of minus a half, or we could use the fact that it's an odd function and change that to, what would it be? Plus the inverse sine of positive a half. Either way, I worked out the inverse sine of minus a half, so I've got pi on 4 minus pi on 6. And we get 5 pi on 12. The cosine of the inverse sine of 40 on 41. What you always got to remember is the inverse trig of something, you're talking about an angle. So this is saying the cosine of the angle. You don't have to go and find the angle. The way I do it is I'll just draw up a triangle and I'll say, oh look, it's that angle down there. Like, I don't know what it is, but that angle is going to be the inverse sine of 40 on 41. So therefore, opposite over hypotenuse is 40 over 41. Bit of Pythagoras, I get the other side. So now the question is saying is, what is the cosine of that angle? And I can read off it and go, oh, well, that's 9 on 41. Okay? So you don't have to find the angle. Do one the other way around. The inverse sine of the sine of 5 pi and 6. It is so tempting to say the answer is 5 pi and 6. Because inverse sine and sine cancel each other out. It's not 5 pi and 6. And the reason it's not is because inverse sine, its range was minus pi on 2 to pi on 2. It can only give answers in between minus pi on 2 and pi on 2. So we have to think, what is going to be the equivalent one? Sine of 5 pi on 6, positive or negative? Think about which quadrant it's in. Right, so therefore, it will be the same as the sine of pi on 6. So that will give me the answer pi on 6. If I had ended up in, say, the third quadrant or the fourth quadrant, then I know it would be minus pi on 6. That's the way I tend to think about those ones. So be real careful. So if it has got an acute angle there, it's not an issue, because they will cancel out. But once we get past acute, we have to think about the actual range of the function itself. We've got to get the answer in that range. Okay. Sine of 2 times the inverse cos of 3/5. The inverse triggers an angle. So all this is really saying is sine 2 theta. Well, that's 2 sine theta cos theta. So let's make it even easier. We'll say, okay, theta is the inverse cos of 3/5. It's going to be whatever that angle is. Draw up a triangle. I'll let that angle be theta. Adjacent over hypotenuse, 3 over 5. So that's just our nice 3, 4, 5. Okay, so that's going to be 2 sine theta cos theta. I'll just read off the triangle. And so 2 times 4/5 times 3/5, we get 24 and 25. The inverse cos of 2 cos pi on 3. So this is the other way around now. We're finding the inverse cos of a double ratio. We don't have a formula for that. But fortunately, I've given us an exact value there we can work out. Cos pi on 3. So that's the same as saying 2 times a half. Inverse cos of 1, which is just 0. We talk about 2 angles here. They're not in the same triangle. So don't try and fit them into the same triangle. We've got 2 things here. So we can say, well, look, alpha is going to be the inverse sine of 2/3. We'll draw a triangle for that one. Beta, inverse cos of a quarter. Let's draw a triangle up for that. And now, tan plus tan on 1 minus tan tan. Let's sub in and play around with all our ratios. And eventually we get, whoa, what a great expression. 2 plus 5 root 3 over root 5 minus 2 root 15. Feel free to rationalise the denominator if you wish. So 1b, playing around with these inverse trig and manipulating them to get answers.